Now we're going to do some derivatives that involve logs with arbitrary bases. The first thing we want to do is remember that change of base formula. So if I have log base 8 of x squared minus 7x, what I'd rather do is rewrite that as 1 over the natural log of 8 times the natural log of x squared minus 7x. So if I need to take the derivative of this function, what I'm going to do is I'm going to say I'm going to rerun it that way. Now this is just a constant, so it doesn't matter. Like, we can pull it out. We don't have to worry about its derivative. So we say 1 over natural log of 8 times the derivative of natural log of x squared minus 7x. Now what we need to do is take the derivative with the natural log, which is something we already know how to do. Remember that the derivative of the natural log is 1 over something times the derivative of that something, right? That's the chain rule. So it's 1 over natural log of 8 times 1 over x squared minus 7x times the derivative of this, which is 2x minus 7, giving us an answer of 2x minus 7 natural log 8 x squared minus 7x. Simple enough. So, logarithmic problems with arbitrary bases really are no different than logarithmic problems with the natural log. They just end up with this extra constant in front related to the base. So don't overthink it. Now this is a really interesting problem. This is going to use something called logarithmic differentiation. And logarithmic differentiation sounds really complicated, but all it is a method of implicit differentiation that allows you to kind of be clever with how you do stuff. So just bear with me here. If I know that y equals x to the 4 over x, and let's just say that I know a little bit about x, that I'm not going to end up with negative values that come out of this, and I shouldn't, but if I say x has to be greater than 0, for instance, I can say the natural log of y is the natural log of x to the 4 divided by x. Then I can use the power rule for logs to write this as the natural log of y is 4 over x times the natural log of x. So in doing that, what I can now do is I can take the derivative. So I can say the derivative of this, of both sides, well, the derivative with respect to x of this is, remember the derivative of the natural log is 1 over the log times, 1 over the argument times the derivative of the argument. So it's 1 over y times y prime, okay? Now the derivative of this is going to be a product rule. So we're going to say that's the derivative of 4 over x times natural log of x plus 4 over x times the derivative of natural log of x. So when we take this derivative, we get 1 over y times y prime is negative 4 over x squared natural log of x. Right, if we take that derivative, hopefully you're comfortable enough to see going here to here. If not, you'll write that as like 4x to the negative 1 and then go from there. And then this is 4 over x times 1 over x, which then becomes 1 over y times y prime negative 4 over x squared natural log of x plus 4 over x squared. So I see I have a 4 over x squared in each term, so I'm going to factor that out. So I'm going to say 1 over y times y prime is 4 over x squared, 1 minus natural log of x. It's just cleaner to write it that way as opposed to negative natural log of x plus 1. But here's the problem. We have this 1 over y prime. What we really want to get is y prime by itself. So I can multiply the y over. and say that's y times 4 over x squared, 1 minus natural log of x. That's really unsatisfying because I have y prime in terms of y. I want y prime in terms of x. So what I have to do is I have to go back to the original problem statement. And I say, I know that y is equal to this thing. That's the definition. I mean, that's what we started with. So instead, I get x to the 4 over x times 4 x squared 1 minus natural log of x. And that's how you take the derivative of that, which is really neat.